Let's begin. So this is chapter 3, and a transistor can function as a switch or an amplifier. And there are two types of transistors that you will learn in this course, KL 2174. The first type is BJT, which is an acronym for Bipolar Junction Transistor, and the second type is the FET transistor, or the full name is MOSFET, which stands for Metal Oxide Semiconductor Field Effect Transistor. Now, a BJT is a three-terminal semiconductor device. Similarly, MOSFET is also a three-terminal semiconductor device, but you will learn more about MOSFET in later chapters. Now, a BJT has three terminals, and the names of the terminals are listed here. They are emitter, base, and collector. And each of the terminal can be an N-type or a P-type semiconductor. If you recall, and you should have watched my first online lecture, which I posted in the Facebook group, a semiconductor material, and for our course it is silicon, can be an N-type or a P-type. Now, because of the different configurations of how the P and N-type can be arranged, we have two types of transistor. We have two types of BJT. We can have the PNP type or the NPN type. Alright, and you can see the three terminals here. There's the E for emitter, B for base, and C for collector. Alright, in both cases, whether they are P on P or NPN, you should notice that the base terminal is significantly thinner than the emitter or the collector. Right, the base terminal is thinner than the emitter or collector, and there's a reason for that, which I will explain later on. Now, what do transistors do? Now, the first function of a transistor is a switch. By analogy, you can look at this example, how our transistor function as a switch. So imagine that you have a long pipe, and you pour some water from the emitter. So you pour some water into the pipe from the emitter, and the water is supposed to go down all the way to the collector. But before they can get out of the collector, they will have to pass through some sort of a valve, and this valve is controlled by the base. So if the valve is open, the water can go through. If the valve is closed, the water cannot go through. So that's how it essentially acts as a switch. What input signal you apply at the base determines whether or not you can get some output or not. Alright, so if you open the valve, you get some output. If you close the valve, by turning the base, you will not get any output. So that's a switch. Alright, so the current flow from emitter or collector is switched on or off. It is controlled by the base. Right. Now, this is an example of how a transistor functions as an amplifier. It's the same example. You have a pipe, but the construction of the pipe is a little different. Water coming from the collector will go through a thinner region here, and that region here, there's a valve in the thinner region, and the valve is controlled by an even smaller flow of water being pumped into by the base, right? So if you pump some water into the base, right, the valve will be lifted and a huge flow of water can flow through, right? If you don't pump any water into the base, the valve will close and no water comes out. If you apply a lot of water, the valve opens relatively bigger, you can get more water coming out. So what happened here is that a small input applied at the base, small input meaning that the water that you pump into the base is smaller. You can see that the diameter of the pipe of the base is smaller than the diameter at the base. The pipe at the base is smaller than the diameter of the pipe connecting the collector and emitter. So a small input you apply at the base controls a bigger output coming out of the emitter. So in essence, you are actually amplifying the signal, the input that you apply in the base. You control a bigger amount of current using a very small amount of you control a big amount of current flowing from the collector to the emitter using just very small of current being pumped into the base. So essentially, a small current controls a small input controls a big output. So the base current is amplified. So I hope you can understand that two very simple examples of how transistor performs as a function and a switch. Now this is a simple circuit showing you how does a transistor function as an amplifier. This is a simple amplifier circuit with a transistor, and the transistor is over here. This is the symbol of a transistor. Now I would like to ask you one question. What type of transistor is this? Is it NPN or PNP? What is it? Yes, that's right. It is a PNP transistor. How do you know? Because the current at the emitter here, this is the emitter terminal, the direction of the arrow is pointing in. So that's why it is a PNP transistor. Now let's see how does the transistor work in this circuit. So you have a transistor here, and at the input side you have a microphone, and the output side you have a speaker. So what happens is that when you speak into the microphone, the vibration, the air vibration will make the diaphragm vibrates inside the microphone, and that will turn your voice into small signals, small vibrating signals, small AC signals, and that signal is very small. It cannot be used to drive the speaker, so that signal must be amplified. So your voice is converted into tiny electrical signals, and that signal will travel through the capacitor, and you should know why, because capacitor acts as a short circuit to AC, right? So that signal will travel right into the base of the transistor, and the transistor will amplify that tiny electrical signal. It will be magnified, and the output will come out at the collector side, and the output signal, the amplified output signal, is being fed into the speaker, and as a result your voice is now amplified. Now let's look a little closer into the construction of a transistor. You have the PNP type over here, and you have the NPN type over here. And for both types, again, the base are located in the middle. The base terminal is located in the middle, and it is thinner than the collector of the emitter. And also you can also recognize whether the transistor is PNP type or NPN type by looking at the arrow indicated on the emitter terminal. So if the arrow is pointing in, you are having a PNP type transistor. If the arrow is pointing out, you are having an NPN transistor, and the arrow is always located at the emitter terminal. Now this slide shows you more terminology associated with PNP and NPN type transistor. Now as I've mentioned to you just now, the arrow is always drawn on the emitter, so you can see the arrow always on the emitter terminal, whether it's PNP or NPN. And for PNP type, the arrow is pointing in. For NPN type, the arrow is pointing out, and the arrow indicates the direction of the emitter current. So for a PNP transistor, you have the current coming from emitter into the base, and for NPN type transistor, you have current coming from the base terminal going out into the emitter. And there's also some other terminologies associated with the current. Now IC is the collector current, so it's over here, that's IC, and IB is the base current, it is at the base, and IE is the emitter current, it is located at the emitter. And please take note the direction of each of the currents with regard to whether they are PNP or NPN type. Now let's connect our transistor with external battery sources. Now in this example I'm using a PNP transistor, but the basic principle is the same. Basic principle of operation is the same regardless whether it is a PNP or NPN type transistor. Now in this example you have the PNP type, and the emitter and base is connected to VEE or V emitter, and the base and collector is connected to VCC or V collector. So immediately you should be able to see that the base and emitter junction is forward bias. You can see that the emitter is P-type and it is connected to the positive terminal of the battery, right? And the base and collector are reverse bias because the collector terminal is P-type, but it is connected to the negative terminal of the VCC. Now let's examine what happens where at a base emitter terminal and base collector terminal individually. So let's take out the base collector terminal first, and let's see what happens at the base and emitter terminal when we connect them to a battery. So because the base and emitter terminal is reverse bias, so basically what happens is you have current flow, and because they are forward bias, you know, the P-type is connected to the positive terminal of battery, N-type is connected to the negative terminal of your VEE. So this junction basically acts as a short circuit. So you will have a current flow from the emitter into the collector, and in this case the majority carriers are holes. Holes will be drifted into the emitter, and holes from the P-type emitter will be driven into the base, and electrons from the N-type base will be drifted into the emitter. So that's what's happening in BE junction, the base emitter junction, and they are forward bias. Now let's look at what is happening in the base collector terminal. So let's take out the sources. Let's take out the VEE, and let's just concentrate what happens at base and collector. Now for base and collector, the situation is different because the base and collector is reverse bias. You can see that the collector is P-type, but it is connected to the negative terminal of the battery. So you do not have any majority carrier flowing in this circuit. You only have minority carriers, and minority carriers are holes in the N-type material. So holes will be attracted to the negative to the collector because you are applying a negative terminal of the battery at this side. So holes are positively charged, they will be attracted to the negative side. But because they are minority carriers, minority are not many, you know, so in effect you are actually having no current at all. The current which is caused by minority carriers is negligibly small. So what happens when you put the the two sections together? So what happens is that initially we can start our analysis from the emitter. So because the base and emitter junction is forward bias, so majority carriers, which are holes from the emitter, will flow into the base terminal, right? But as soon as they get into the base terminal, they have two options. The holes have two options where they can either exit through the base or they can go straight on to the collector. So which path do you think the holes will take? Sorry, I can't hear you. Of course, they will go straight to the collector. Now you remember I told you that the base is significantly thinner than the emitter or the collector, right? So because the base is so thin, it means that the resistance is higher. So therefore, the base, the holes will not opt to go through the path which have higher resistance. Instead, it will go through straight to the collector, because, and there's another reason why the holes will go through the collector, because as soon as they get into the base, they will see a very high electric field across the collector and base junction, and that electric field is coming from this negative terminal which you apply at the collector. So holes which are positively charged, as soon as they enter the base, they will see one path which has a very high resistance, and at the same time they will also see another path which is a very high electric field coming from the collector. So many of them will be attracted to the collector side because of the electric field applied, because of the negative terminal applied at the collector. But there will still be a little, some of them will still exit through the base, and the range is usually, the current in the exiting through the base is usually in the range of microampere. The current coming out through the collector is usually in the range of milliampere. So the difference is about 100 times more. It can go from tens to hundreds of times more. Now, in order for you to understand, maybe at first it is quite difficult for you to understand transistor operation. So that is why I suggest that you go through this website here. The link is provided here. Just click on that link, and there's a very nice animation which you can play around, which I hope you can help you to understand what happens to the carriers inside the transistor when you bias it differently. So there are two parameters which you can play around here. First is the VBE, what happens when the VBE is less than 0.7, and what happens as you increase the VBE to 0.7. And there's also another parameter which you can play around in this animation, is the VCE, or collector voltage, whether you can turn on or off. And there's a very nice there's a very nice explanation that will be displayed whenever you change your parameters, whether it is VBE or VCE. So please have a look. Just click on the link which I provide here and play around with the animation. Right, so now that we understand the principle of operation, how does a transistor work, it's time to analyze it using the tools which we have learned before in circuit 1 and circuit 2. And we can start by applying Kirchhoff's current law. If you look at the current flow when the transistor is biased, you see that emitter current exiting through the emitter is composed of the base current and the collector current, right? So IE is equal to IC plus IB. The emitter current is equal to collector current plus base current. But the collector current comprise of majority current and minority current. But for our purposes, for this course, we will neglect the contribution coming from the minority carriers. We will just concentrate on the majority carriers. So IE is equal to IC plus IB. Right, so here's a few more terminologies for you to get familiarized with. This is a transistor, and it is currently being biased. This configuration is called common emitter configuration, which I will explain later on. But I just want you to get familiarized first with the terminologies. So VCC is the voltage source connected to the collector. VBB is the voltage source connected to the emitter, and in each of the terminal you have current. So IB is the base current, IC is the collector current, IE is the emitter current, RB is the resistor connected to the base, RC is the resistor connected to the collector. And later on you will also find some other configuration whereby you will have a resistor connected to the emitter, and that resistor is commonly named as RE. or emitter current. Another terminology you should be familiarized is the voltage, the voltage across the terminals. So VBE is the voltage across the base and the emitter terminal of the transistor. VCB is the voltage across the collector and the base terminal of the transistor. VCE is the voltage across the collector and the emitter of the transistor. Now, there are three ways of how a BJT, of how a transistor can be configured or can be connected. And the three are common base, common emitter, and common collector. Now, let's learn about common base configuration first. The reason why it is called common base because the base terminal is common to both the input and the output. And for common base configuration, the input is the emitter current and the output is the collector current. Right, so this is the input side, this is the output side at the collector, this is the input side at the emitter, and both of them share the same common node at the base. So now let's look at the input and output current voltage characteristics. Now for the input side, you are looking at the I emitter because IE is the input current and VBE, which is the input voltage, right? So you can see here that when VBE, your input voltage is very small, when it is less than 0.7, the current is very small. It is almost zero. But as soon as your VBE increases to about 0.6 to 0.7 volt, you have an exponential increase in IE. Your input current increases dramatically. Alright, but you see that the output voltage has little effect on the IE. VCB, V collector base is the output voltage, and whether or not it is small or big from 1 to 10 to 20 volt, you see that there is not much difference in the IE. So VCB has very little effect on IE, but it should be instantly clear to you what does this curve look like. This curve looks like your diode IV characteristic, isn't it? For a silicon diode, when the diode voltage is less than 0.7, the diode is not conducting, so it is 0. But when your diode voltage is more than 0.7, the diode is conducting, which makes sense because if you look at it again, if you look at the if you look at the base emitter, right? This is the base, and this is the emitter junction. It is a diode. It's a PN junction, and it is forward biased by VEE. Okay, so that's why when you measure the input, when you plot the input characteristic, okay, that's why when you plot the input current and voltage characteristic, you get a diode characteristic. You get a silicon diode characteristic, whereby you can see that the current is 0 when the input, the VBE, the biasing voltage is less than 0.7. Now let us look at the output side. Let us look at the output current voltage characteristic. So IC is your output current, right? So and VCB is your output voltage, and these curves here, these individual curves here are your IE, your input current, right? So it should be immediately clear to you that, let's say you pick a point, let's say at VCB equal to 10 volt, and you give in input current of 1 milliampere, you get 1 milli. If you input, you give an IE of 1 milliampere, you get 1 milliampere of output current at IC. If you increase your IE to 2 milliampere, you get your output current at the collector side of 2 milliampere as well. If you further increase your IE to, let's say, 6 milliampere now, you also get IC is 6 milliampere. I collector, which is I output, is 6 milliampere. So you can make a generalization that I collector for common base characteristic, for common base configuration transistor, IC is equal to IE. It's almost equal to IE. Alright. And I want to explain a little bit about these regions of operation. Down here you have cut-off region. The reason why it is called cut-off region is because the transistor is not operating. It is turned off because your input current is less than 0. So this is IE0. When you give 0 current to input, you get output current 0, right? And this is the saturation region. Saturation region is this knee points here. How you read it? How you read this region is that you begin by 0 at the 0 point, and let's take one level of IE. Let's take this 2 milliampere to 2 milliampere curve, and let's look what happens. So you are supplying IE of 2 milliampere into the transistor, and as you gradually increase your output voltage VCB to a little bit nearing 0 volt, so your output current IC will initially increase, right, up until this point, up until 2 milliampere, and after that, if you further increase your VCB, you will not get any more increase in the IC, right? So this is the point where your transistor is said to be saturated. It does not give any more increase in output current. In order to get a further increase in output current, in order to get a further increase in IC, you have to increase the amount of IE. You have to increase the amount of emitter current, the current that you give into the transistor. So this slide tells you the regions of operation which I have explained to you just now: active, cut-off, and saturation. So for cut-off, the base emitter and collector base are reverse biased. The transistor is off, very little current flowing through the transistor. Saturation region, the region with exponential increase in collector current, whereby the base emitter and collector base are forward biased. And the active region, I forgot to show to you just now. The active region is this region here, right? The region sandwiched between the saturation and the cutoff. So ideally, you want your transistor to operate in this active region, right? If you want your transistor to work as an amplifier, you would want your transistor to operate in this active region. If you want your transistor to operate as a switch, 1 or 0, switch gives an output of 1 or 0. You have to operate your transistor, you have to switch your transistors of operations between saturation and cutoff. So when it is 0, when you want your switch to give out 0, you should operate your transistor in cutoff region. And you want your transistor to, when you want your transistor to turn to your switch to turn on or giving an output of 1, you should operate your transistor in the saturation region. Now let's analyze our transistor with some mathematics, some mathematical modeling. I have shown to you just now why IC is equal to IE. I collector is almost equal, it's not equal, it's almost equal to IE, and the reason you can see from the graph which I have shown to you just now. So let's take an IE of 2 milliampere, you get an IC of 2 milliampere as well. If you give your IE of 5 milliampere, you get an IC of 5 milliampere as well. So IC is almost equal to IE. And another reason for that is because I base, the current coming out through the base is very small. Current going out of the base, if you remember the reason why current coming out of the base is very small, because most of the majority carriers are mainly attracted towards the terminal side. They see a very large electric field coming from the collector, so very little of the holes will exit through the base. Furthermore, the base is a very resistive area, so it will not come out through the base. So I base is usually in the range of milliampere. I collector is in the range of milliampere, right? So we can usually approximate IC is equal to IE, and the base emitter voltage is 0.7 volts. This is the turn on voltage for a silicon diode, You should know that already by now. And I want to introduce to you the alpha constant. I don't know how. Alpha coefficient here. Alpha coefficient is the ratio of IC over IE. So alpha, you get it by calculating the ratio of IC over IE. And ideally alpha should be 1. But in reality you get a value of very close to 1. It is 0.9 to 0.998. Why is it very close to 1? Yes, very good, because we have determined already. We know that IC is equal to IE. It's almost equal to IE. So if you divide IC over IE, which is almost the same magnitude with each other, you will get nearly 1, right? So to calculate alpha for DC, you just divide IC the DC and IE DC. But for alpha AC, you divide the range of the values of IC, delta IC divided over delta IE. Another coefficient which I want you which you should know is the beta coefficient. Beta is IC over IB. It is a measure of current amplification. You can see from the mathematics itself, it's a measure of how big the collector current compared to the base current. Okay, and this is an example of a common base amplification. An example of how a transistor in a common base configuration is used as an amplifier. So the input voltage is just 200 millivolts, and the input voltage is seeing an input resistance, an input impedance of 20 ohm. At the output, you have a resistor of 5 kilo ohm, and the output resistance looking from the output into the transistor is about 100 kilo ohm. Is 100 kilo ohm, sorry. So you are asked to find what you are interested to find what is the voltage gain, V out over V in. So you start by calculating what is the input current. So input current is just V in over R in. So V in is 200 millivolt, R in is 20 ohm, so you get an I in of 10 milliampere, right? And you know that IC is equal to IE. So your I in is actually your IE, is your emitter current. And you know that in common base configuration, I collector is equal to IE. So you can make that assumption. You can use that assumption that IC is also equal to 10 milliampere, which is equal to IE, right? So the voltage drop at the load is then just your IE multiplied by your R load. So 10 milliampere multiplied by 5 kilo ohm of your output load, you get 50 millivolts at the output. So the voltage gain is just output voltage divided by the input voltage. 50 millivolt divided by 200 millivolt, you get a voltage gain of 250. Right, so this is the second way of how the second method of transistor configuration. If you remember that you have three ways to configure a transistor, three methods of transistor configuration, which is common base, common emitter, and common collector. So the first example that we studied just now was common base configuration. Right now we are studying common emitter configuration, and as the name implies, common emitter meaning that the emitter terminal is common to both the input and the output, right? And for common emitter configuration, the input is your base, the signal, the current, and the voltage which is fed into your base terminal, and the output side is the collector emitter terminal. Alright, and the common emitter configuration is commonly used as a voltage amplifier. Okay, now similarly, let's do the input and output characteristics just like we did for the common base configuration. Now let's start with the input characteristic first. Again, it looks very familiar. This IV curve looks like the IV curve of a diode, right? When your BE, your input voltage, is less than 0.7, no current flows in. But as soon as they get bigger than 0.7 volt, as soon as your VBE, your input voltage, grows bigger than 0.7 volt, you start having current, you start having IB. IB, the base current, is now your input current. And again, the output voltage, the VCE, has very little effect on the IB, on the output current. So again, this looks, you should be familiar with this curve already. This is a current voltage characteristic for a diode, which is what a BE terminal is. The base and emitter terminal is a forward bias diode, forward bias PN junction. Sorry. Now let's look at the output terminal. Now for the output terminal, again, you can see the saturation over here. You can see the cutoff region over here, and there's the active region. But what's different between this output, the output characteristic of common emitter and common base, is that the input current is now your base current. So each of these lines here show you your base current level, right? This is your base current level. Each of these lines give you the base current level. So if you are applying a 10 microampere of IB, your base current, you will get about 1 milliampere of the output current at the collector. If you apply about 20 microampere of base current as the input, you will get at the output side at the collector current is 2 milliampere. It should be immediately clear to you that by now that the scales are different. The base currents are in microampere, right? All of them are in microamps. The output current coming out from the collector is in milliampere, right? And also you should also note that there is a little curve, there is a little slope on each of these lines, each of these base currents, indicating the influence of VCE to the IC. So again, let's look at the current relationships for a common emitter amplifier. Again, the emitter current IE is equal to IC plus IB, which you can probably see from the graph here. Yeah. So IE current going out of the transistor to the emitter is composed of IB plus IC, right? So IE is IC plus IB. Again, the same relationship holds for common emitter amplifier. IC is related to IE by alpha, by coefficient alpha. So IC is alpha IE, so alpha is IC over IE. But in reality, there's also a minority collector current, but we disregard that for our purpose in this course. Again, beta, you also use beta for common emitter configuration. It is IC over IB. It is a measure of current amplification. How big is IC over IB? Okay, so for and then there's a DC beta and there's a AC beta. DC beta, you just pick the quotient point, the Q point at which you bias your transistor. So because IC and IB is fixed, you get beta DC. But for AC, you are applying a varying amount of IB. So that's why you use the symbol here, delta IC. So beta AC is delta IC over delta IB at the constant VCE. Now let's look at an example to calculate beta for a common emitter amplifier. So beta DC is calculated. Beta is IC over IB. So you pick a point, any point. The Q point is given in the graph. So the Q point, the operating point for this transistor, is at that point over there. I hope you can see it. So IB at that point is 25 milliampere, and IC is about 2.7 milliampere. Sorry, IB, the input current is about 25 microampere, and IC, your output current, is 2.7 milliampere. So IC over IB, 2.7 milliampere divided by 25 microampere, you get about 108 of beta in DC mode. But when you want to calculate beta for AC, you are applying a range of base currents. For example, your minimum current may be about around 20 microampere, and your maximum current applied to the base may be around 30 microampere. So as a result, you get a range of output current as well at the collector. You get IC1 and IC2. So you do the calculation. Beta for AC is delta IC over delta IB. So maximum current you get from that the range of current base current you apply for this in this particular example is 3.2. The minimum is 2.2. Divide by the range of the delta in your IB, which is the 30 microampere, divide minus 20 microampere, and you get the beta AC of about 100. And you should notice that the beta for DC and AC is close to each other. Right, these are some other relationships relating beta and alpha, which you should memorize. Alpha is beta. Alpha is related to beta by these equations. So alpha is beta over beta plus 1, beta is alpha over alpha minus 1, and the relationship between current is IC is beta IB, which you can get by the very definition of beta. Beta is IC over IB, so it's just an arrangement, rearrangement of beta. Beta is IC over IB, and IE is beta plus 1 IB, which you can derive by using this relationship here. IC is beta IB, and also from the fact that IE is very close to IC, and I will leave that to you as an exercise to derive. Now the final transistor configuration which we're going to learn is the common collector configuration, right? And you should be able to guess by now that the reason why it is called common collector is because the collector terminal is common to both the input and output. And you can see for both cases, whether it's PNP or NPN, the collector terminal is common to both the input and the output. So the input remains the same. The input is the base terminal, the current and voltage being applied at the base, and the output is the collector and emitter terminal, the CE junction, sorry. So because they are just the same, your common collector and common emitter is basically the same configuration. You are just basically switching the rules of collector and emitter. For common emitter, is the emitter which is at common node. For common collector, it is the collector which is at the common node. So you can expect actually the output and input, the input and output characteristics are the same. So the only difference is that for a common collector, the vertical axis here should be IE. Sorry, this is the wrong graph. It should be IE here, and the input voltage is the input current remains IB. Okay, so that's the only difference between common collector and common emitter in terms of the input and output characteristics. Input characteristics remain the same. Output characteristics is now you are measuring IE instead of IC. Now I want to talk about the operating limits for each of the configuration. So this is the output characteristic of a transistor, and there's a saturation region which I've explained to you, and there's a cut-off region, right? And there's a safe operating region which is limited by the maximum power. So if you operate your transistor in the cut-off region, your transistor is not conducting, so it is off. If you operate your transistor in the saturation region, your transistor is on. But ideally, you want your transistor to operate in this white region here, only in the white region here, which is the active region, because when you operate your transistor in the active region, you can vary the input current, which is the IB, and you can get a varying amount. As a result of that, you get a varied amount of IC at the output current. So you can, if you operate your transistor in the active region, you can operate your transistor as an effective amplifier. Okay, and if you operate your transistor outside of the active region, if you operate your transistor in this region here, it will operate outside its safe operating region, because in this region here the transistor is operating beyond its recommended current, recommended wattage, recommended power dissipation. So power dissipation for common base is VCB multiplied by IC. Power is V times I, right? So for common base, VCB times IC. For common emitter, VCE times IC. Common collector is VCE times IE. So when you buy a transistor from a manufacturer, they will give you this graph, and they will give you a maximum safe operating region. So that safe operating region is this boundary here. If you operate outside the if you operate outside this region, if you operate in this uh, in this region outside the active region, you are operating beyond the the recommended current and voltage for that particular transistor. Okay, and this is a typical transistor specification sheet. And what happens is that there's a maximum rating listed in the sheet: maximum CE voltage, maximum BE voltage, maximum collector base voltage, yeah, and also the thermal characteristics of the transistor, and the total power dissipation at a controlled environment, usually at 25 degrees Celsius, and some other information, small signal characteristics, and on and off characteristics. These are all in your transistor, and a transistor can be tested by using these common equipments which can be found in your lab, which are curve tracer, digital multimeter, and ohmmeter. Right, that's it for our lesson, for our introductory lesson on BJT. Next week, the lesson after this will be how you on DC biasing, on biasing a transistor, how do you give power to your transistor so that it operates in the active region. You want your transistor to operate in the active region, and there's a method on how you do that. Right. What I want you to do now is to go. I would strongly recommend to you. These are online lessons on BJT which I found on YouTube, and I think there are many lessons available on YouTube. But I think these three will be very helpful if you can go through each of them. And finally, I want you to do these assignments for tutorial. It's at the back of chapter 3. Please do these six questions, and I will randomly pick any of you to demonstrate the solution during tutorial. Alright, if you have any questions, please feel free to ask me during the lecture or tutorial. And if you that's it. Thank you for your attention. See you whenever I see you. Bye bye.